Okay, in this presentation we are going to look at the geometric distribution. Now this ties in with a couple of other distributions we're looking at, but in this instance we'll just sort of go with what we have. It also features conditional probability as well, so just be careful about that. Mindful of that, I should say, rather than careful. So coin 1 is an unbiased coin. Okay, so when tossing a coin, the probability of getting a head is 0.5. Okay, coin 2 is a biased coin, so when you're tossing the biased coin, the probability of a head is 0.6. Okay, so 0.5 for the fair coin, 0.6 for the biased coin. So one of the coins is chosen at random. Then the chosen coin is tossed repeatedly until a head is obtained. Suppose that the first head is observed in the fifth toss. Determine the probability that the chosen coin is coin 2, the biased coin. Okay, so what we're going to do here is use the geometric distribution, okay, which is what we should use here. That in this particular instance, that gives the probability that the first occurrence of a success requires k independent trials, each with a success probability p. Now just be careful about the geometric distribution because there's a different way of stating the geometric distribution in terms of the number of failures before the first success. They're very similar, but the construction is a little bit different. Okay, so just be mindful of that. So if the probability of success in each trial is p, then the probability that the kth trial out of k trials is the first success is as follows. The probability of x equal to k equals 1 minus p to the power of k minus 1 times p. Okay? So what we're going to do is calculate that for the fair coin, which is 50-50. 50% heads, 50% tails. So the probability of x equal to 5 equals 1 minus 0.5 times 5 minus 1 to the power of 5 minus 1. Okay, which is to the power of 4. 0.5 to the power of 4 times 0.5. So that works out to be 0.5 to the power of 5. That is 0.03125. Okay, so for the biased coin, probability of x equal to 5 equals 1 minus 0.6 to the power of 5 minus 1. So that's 0.4 to the power of 4. That is times 0.6. So what we end up with is 0.4 to the power of 4 times 0.6. Okay, so you can disregard that. That's a little typo there. So that should work out to be 0.01536. Okay, and you can just disregard that typo. So what we're going to do here is use conditional probability, calculate the probability that it is coin 2 given that we're dealing with the fifth toss. So it's a conditional probability. So 0.01536. Okay, that is the probability that it was coin 2 and the fifth toss, divided by the probability that it was on the fifth toss. So 0.051536 plus 0.03125. So that should work out to be 32%, 0.3295. Okay, so that's grand. We'll leave it there. Straightforward enough one.